Today I want to look at calculating fluid force using integration. So here I have a picture of a container. Imagine this is filled with water or some other liquid. And the thing about fluids is the force in the fluid is distributed equally in all directions. So you can think of, I like to idealize it, think of it as individual drops of water. That drop of water is pushing down on this one. Instead of like a solid just pressing straight down, that'll push out in all directions equally as well as down. So what you have in a liquid is all of this liquid in the middle is balancing each other out. This little dot's pushing on this one, but it's pushing back. But once you get over to the edge here, this liquid will be pushing on the edge of the container. So if you're standing there with a glass and there's water in it, and all of a sudden that glass disappears, the water's not going to just sit there in that shape. It will push out and fall out of the container that's no longer there. So what we're interested in is not all this internal canceling of water on water, but at the edge here, how much is that fluid pushing on the edge of the container? So before we get into that, let's talk a little bit about fluid force and pressure in general. First of all, some terminology for pressure. Which I'll use rho for that. Pressure is just force per area. So that rho there is pressure. F is force, and A is area. Okay, so if we're thinking about a fluid, if you were looking at the very bottom here, you'd have this little speck of water pushing on this, pushing on the next, and it's an additive effect, right? The weight of that little dot of water is pushing down on this one, but now both of their weights are pushing down on the next. So if we were interested in the bottom of a container, and let's just make a very simple diagram here. Where we have some area there. I have this rectangular solid full of liquid, has some area in the base, and some height there, h. And say this is filled with liquid, where W is the weight density. The force on the bottom of that square there on the bottom would simply just be the weight of the water above, right? You have all this water, it's pushing out to the sides as well, but as you stack all that water up, at the bottom you would just have the net weight of all the water above, and that's a simple algebraic calculation, right? If we wanted that force on the bottom there, well, how much does this water up above weigh? It has some volume, and it has some weight density. So volume times weight density would be the weight. Well, what is the volume of this container? It's got base A and height h, so we could write this as AHW. So all the water at this bottom here, the total force on there is this AHW. If we wanted to express what was going on in terms of force per area, that would be our pressure. So pressure is force per area, which force we just said is AHW. So pressure is simply your depth, h, times the weight density. Notice it has nothing to do with the shape of this container, just how far below the surface of the water you are. This h is really how far underwater we are. We've all experienced this in everyday life. You go swimming, the farther down in the pool you go, you feel that pressure on your ears. And that pressure has nothing to do with how big that container is, right? Jumping into a backyard pool versus an Olympic-sized pool versus the ocean, doesn't matter how big that container is, you still feel the same pressure in your ears. It's really just a matter of how far underwater you go and the weight density of that particular liquid. Okay, so we've got this calculation for force. If we were just all at a single depth, it would just be the area of that square, depth, weight density. And if we were interested in just per unit area, that's pressure, depth times weight density. So far, no calculus. Why does calculus come into this? Well, if we're looking at the side of this container or the side of this container, the problem is, as we move down the side, if we were interested in how much that fluid is pushing out on the side of that container, we see that force is a function of depth. So if you're right here on the container versus here, versus here, versus here, every little spot along that edge as you go down and down and down, you have more and more pressure, or therefore more and more force. So in order to determine how much that liquid is pushing on the side of the container, we're going to have to, as you may have guessed already, like we've done with everything, we're going to have to slice that up, right? If we take a thin slice, that thin slice we can idealize as thinking of it as all being at one depth. Even a thin slice obviously is not all at one depth, but that'll be our approximation. If we're interested in fluid force on the bottom of a container where the entire surface is at one depth, there's no need for calculus, it's simply algebra. But once we're looking at the sides, because of that varying depth, we're going to need integration. So the easiest way to go through this is we'll start with an actual example, and that's what we'll look at next time.